All right, welcome back, everyone. Good evening, and thanks for joining. So today we're going to continue from where we left off yesterday, which is viewing the error correcting code that we designed in more linear algebraic notation or format. So I'm not sure if there are people who are joining us today who don't have the context from yesterday, so I'll probably just do a quick recap. So we have a common sort of notation and we're on the same page. So our goal was to basically be able to detect errors when a message is transmitted over a noisy channel. And we said we'll restrict our attention to the problem of fixing exactly one error. So that means we identify that there has been an error and we know the precise location of the error. So because we're only talking about bits, once we know where the error is, we also know how to fix it because it's just a matter of flipping it back, right? And here is an example of a setup which involves sending 16 length message. Actually holds a base message of length 11. That's the content that we want to transmit. And it has 5 redundant bits, one of which we have not even specified. So I'm just going to take a minute here. Okay, sorry. So yes, so we have these 5 additional bits, and the way they work is that the orange bit that you see in the third column of the first row captures the parity of all the bits in the last 2 columns. So in particular, so that's one of our redundancy bits. So we get to set it the way we want to. So one way of thinking of it is
Ma'am, are you still speaking? I can't hear you.
Sorry, it appears that my internet dropped out on me. So maybe could somebody let me know what was the last that you heard from me? There was a bit where I said that I'm probably showing you the wrong slide. Did you catch that?
You're not sharing your screen.
Right. Okay. Let me pull up the screen back. Thank you. Let's see. Hopefully, now the screen is back up. So my Wi-Fi did die on me. I'm on my mobile hotspot now. Hopefully, we don't experience any lags. Let's see. Okay, the orange bit was a parity bit was the last thing I said. Okay, so I think I was showing you this slide earlier, which what I was saying was that yesterday we used this as an example to actually work through and find our way to an error. So that's probably not what I want to show you. Let me show you something that's sanitized. This is a valid example where all our redundancies are properly inserted. So all the parity checks actually check out. And continuing with the recap, what we said was that the orange bit is set to ensure that the number of ones in the last 2 columns is even. You could think of it also as just the mod 2 sum of all the entries in the last 2 columns. And similarly, the blue bit is set to ensure that the number of bits in the second and the fourth columns are even. The green bit is set so as to ensure that the total number of bits in the second row and the fourth row are even, and the red bit is set to ensure that the total number of bits in the last two rows is even. That's how these bits were set. And it turns out that setting them this way allows us to detect if something went wrong with the message that was transmitted. For now, we're not doing anything meaningful with the X bit on the top left. What I said I will leave as an exercise is this idea that you can actually utilize that space to figure out if there was more than one bit that was flipped. Okay. For now, we have, we're doing good because we have 4 parity check bits, and we ask each of them. So, for example, suppose this is the message that you receive across the channel. What we are going to do is go to each of these parity check bits in turn and ask them, well, do you have a problem? Are you not set properly, or are you set properly, right? And if you think of these locations, read them from left to right and then top to bottom. So the first row, the first 4 locations are 0, 1, 2, 3. The second row, the locations are 4, 5, 6, 7, and so on. If you think of it that way, what Vinay pointed out yesterday was that you can really think of these parity check questions as doing a binary search to discover the location of the error. So normally what you do when you're binary searching for something in an array is that you try to probe it in the middle and see if the value that you're looking for is on the left or on the right. Okay, so here we have locations ranging from 0 to 15. So let's find out if the flipped bit was in the last 8 locations or the first 8 locations. And we can discover this by querying which parity bit will tell us if the flip happened in the last 8 locations or the first 8 ones. So the last 8 locations are the last 2 rows, and the first 8 locations are the first 2 rows. So which bit should I ask to do like the first step of my binary search process? The red bit, exactly. So the red bit tells us if a flip happened, did it happen in the last 2 rows, or did it happen in the first 2? And the way it informs us about that is in the following fashion. So if the red bit is not set correctly, meaning if the parity of the last 2 rows is off, it's not even, then we know that the error must have happened in the last 2 rows, which seems to be the case here, right? So we have 7 ones across the last 2 rows. So we have basically narrowed our search space down to those 8 positions. So the red bit already reassures us that there has been no hanky-panky in the first 8 locations, so we can hold our peace on that front. Of course, I should emphasize once again that all of this is with the running assumption that only 1 bit has been flipped, or at most 1 bit has been flipped. So if there are 2 bit flips or more, then all bits are off. These arguments will not work out so nicely. So let's assume that at most 1 bit has been flipped. In this case, because the red bit has already reported a problem, we know that this is not an error-free message. We know that there is a bit that has been flipped, and it's somewhere in those last 8 locations. Now, to zero in on these locations further, let's say I want to know, well, is it in the last 4 or is it in the first 4 among the last 8 locations? So basically, I want to narrow down further on whether it's the 3rd row or the 4th row. Which parity bit will tell me whether it's in the last row or the second last row? All right, the green one, that's perfect, right? So the green one tells us about the parity of the 2nd row and the 4th row. And of course, we know that there has been no problems in the 2nd row. So if the green bit reports a problem, then we can reduce the size of our limelight so that it focuses only on the last row. But if the green bit does not report a problem, then we know that the issue was in the second last row. Okay, so in this case, the green bit is happy. There are 4 ones across the second and the fourth row. So the green bit says, well, the last row in particular is clean. There's no problem there. Although if you look at the last row in isolation, please don't get confused about this. The last row in isolation does have 3 bits, but the green bit is holding fort for the last row and the second row combined. So those two together report an even number of bits. So the green bit is overall happy. And therefore, we know that our problem is on the third row, right? So we have narrowed it down to the third row. And now we want to know, well, within the third row, is it the first 2 bits or the last 2? So is the issue in the first 2 columns of the third row, or is it in the last 2 columns of the third row? Which bit will answer this question for us?
The orange bit.
Yes, exactly. The orange bit will tell us, was the problem in the last 2 bits of the third row, or was it in the first 2 bits? Because it's overall accounting for the last 2 columns, and we have already eliminated as suspects everything that's in the last 2 columns and the first row, second row, and fourth row. This we know from our investigation so far. But nevertheless, the orange bit, if it's happy, then we know that the problem must have been in the first 2 columns. And in the first 2 columns, we have narrowed it down to only the third row, so we can just worry about those 2 bits. But if the orange bit is angry, is not set properly, then we know that the issue is in the third row in the last 2 columns, right? So let's look at the orange bit. It's reporting 5 ones across the last 2 columns. So we know that there's a problem. So currently we can now narrow down our suspicion to the last 2 bits of the third row. And now we're basically down to 2 choices. And there's one parity bit that's left that we haven't made an inquiry of. That's the blue bit. The blue bit accounts for the second row, the second column and the last column. And the second column is already free of suspicion. So if the blue bit is not happy, then we know that the problem was in the last bit. But if the blue bit is happy, then we know that the problem is in the second last bit of the third row. So in this case, the blue bit is actually happy. There are 6 ones across the second and the fourth column. And therefore, we know that the issue must have, in fact, been in the third column and the third row. And indeed, that's the error that we did identify. We asked the same questions yesterday, but in a slightly different sequence, because I wasn't really presenting it as a very direct analogy of binary search. But if you were binary searching through an array of length 16, this is roughly how you would progress with your questions. Although here we are not searching for a particular element in a sorted array. We are searching for a location where something may have gone amiss, but the spirit of like the sequence in which the search progresses, hopefully you can see that analogy here. Right, so the minimum number of questions we have to ask is 4, and like you're pointing out in the chat already, it's minimum and maximum. We ask precisely 4 questions to zero in on the target. So we don't need more, because this construction shows you that you don't need more. In particular, if all the parity bits report that they're happy, then you know that there is no error because everything checks out. But if there's any unhappiness at all, then these 4 answers lead you to the scene of crime, like we said yesterday. So now in terms of the minimum maximum, I mean, you could ask for, is there a more efficient encoding, or is there a different strategy where we can ask fewer questions and still transmit messages of length 11 and detect one bit errors? And that's, well, proving that you need at least 4 questions to tackle 1-bit errors in messages of total length 15. That's a different question, and I'm not going to go into that here. I don't know if somebody knows the answer to this. I wouldn't presume. So like I said, there are more efficient codes than Hamming codes in general, but for this particular combination of parameters, I'm not aware of like what's the answer to that question. But with this particular method, so if you fix this encoding, if you ask fewer, I mean, if you examine fewer than 4 of these parity bits, then you will have ambiguity in your search process. So to narrow down the exact location, you do need to ask all of those 4 questions, and you don't need to ask any more. So in the context of this process, 4 is the exact number. In general, it's going to be something log n-ish, depending on, like, you have to be a little precise about the notation for what's the message length, what's the length of the thing that you're transmitting, what's the length of the actual message that you're sending, and so on. But that's kind of the growth of the number of redundancy bits you need to add in. In terms of more efficient, like other more efficient encodings overall, different algorithms, different styles for this particular combination of parameters, that's something that I will have to look up and get back to you, which I will do when we meet over the forums. Okay. All right. So yeah. So now moving on, let's just think of how we can describe what we just
No, I just
discussed.
thought I'll add, if you can go back
Yes.
to your previous slide.
The one with the parity bits
So
pointed
the
out.
reason for the X there is
Mhm.
because if there are no errors at all, right, it would actually point to some
Yeah.
to that particular square, and
Exactly.
so to remove the the top left square, because that corresponds to the fact that everything is good, right?
Yes.
All the boxes actually give you.
Yes, exactly. So I think what's happening here is that a combination of 4 yes/no questions lead you to 16 possible answers. And at a first glance, it might look like there are 16 locations. So each answer will lead you to a particular location. So that seems to be perfect. But that's in a situation if you're guaranteed that one bit is flipped. And then if all the parity check bits check out, then you would know that the X location has flipped. But then the issue with doing it that way and trying to squeeze in one more bit of message in this whole scheme is that you would not be able to distinguish between, has the top left corner flipped, or is it the case that nothing has flipped? So there are actually 17 outcomes that you want to capture if you're actually sending all of these bits across the stream and the top left bit is actually a message bit. In that case, you actually have 17 outcomes, which is, well, the first bit flip, the second bit flip, the third bit flip, blah, 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 up to bit number 16 flipped. And the 17th outcome is that nothing has flipped. So 16 answers will not capture all the 17 outcomes, which is why we kind of threw away that bit, so that if all the parity bits check out, you can say with confidence that nothing has flipped. However, what I was saying yesterday, just to build on Vinay's point here, is that if you use that space, if you're somehow OCD and you like blocks which are powers of 2 and you really want to transmit 16 bits, if you want to use, I mean, if you're willing to introduce one more redundancy bit, what you can do with it is record the parity of the whole matrix, because then what will happen is that you can also parity check the X bit, and if it's fine, you know that, and all the others, so if all the 5 parity check bits are happy, then you can be sure that there are no errors. But if the overall bit is unhappy, then that means, and all the other parity bits are happy, that combination is not possible if there was exactly one bit that flipped, right? Because if there was exactly one bit that flipped, that would make the X bit unhappy, but it would certainly disturb one of the other parity bits at least. So then you know that it must have been the case that more than one bit has flipped. It's possible that I'm missing some nuances in arguing this properly, but I'm reasonably sure that you can set the X bit carefully if you want to. What you gain by introducing one more redundancy or parity check bit is this notion that you can correct up to one bit flip, and you can detect if more than one bit was flipped. That's the hope. But in the basic setting, you can basically throw away the X location and you'll be fine. And this is called, I think it's called 1115 Hamming code, because it takes messages of length 11 and maps them to codes of length 15, because you don't need that X bit. And you managed to correct for up to 1 error. So yeah. Okay, so moving on, how do we record the code or the process that we just went through as a matrix? So, well, let's imagine that we're going to apply our matrix to bit sequences that are our messages. So these are going to be sequences of length 11, right? And what do I want as the outcome of this matrix? Well, I want the string that came out in that 4x4 grid that we just saw. And let me ignore the first location, that was the X bit. Like I said, you could set that to the parity of the whole matrix, which would be an all ones. But ignoring that for a second, the first meaningful row in this matrix. So I'm applying, let me see if this makes sense. So I'm applying the first row in this matrix, which has 11 columns, to the message there. And can you see what is getting pulled out with this row that's going in there? So this row really corresponds to the blue parity check bit, because it's the first bit in my output message. Okay, so what it's trying to capture is all the things that the blue parity bit would be considering. So if we go back here, the blue parity bit considers all the bits which are in the 5th, 9th, 13th, 3rd, 7th, 11th, and 15th locations. So that's 7 locations from the input message. So I'm just trying to capture the indices of that input message, and I'm triggering those to ones in this row. And because this is over F2, it's what this is going to do is it's just going to strain out the bits at those locations, and it's going to add them mod 2, and that outcome is the correct setting for the blue parity bit. So is this translation to the matrix making sense? Maybe I should back up a little bit and tell you what this matrix is trying to do. What we're hoping is that we have this matrix which we can apply to our message. So our message is length 16. Our message is length 11. And when I apply this matrix to a bit vector of length 11, what I want as output is a bit vector of length 16. Right. So I think there's a comment in the chat that this is not clear. So let me maybe explain what this matrix is trying to do. So let me just back up a bit. So I want the matrix to be something that I can apply to a vector with 11 coordinates. Those are going to be my message vectors. And what I want for the matrix to do is output a 16 length vector, which is the vector that we have just discussed. So you can think of this matrix as a program that's generating those parity check bits and putting them in the correct places. So what should the coordinates of the matrix be? I mean, what should the dimensions of the matrix be? You can already see it on the slides, but I just want to sanity check that it makes sense. Here is a matrix or a transform that takes 11 length bit vectors or bit vectors with 11 coordinates and maps them to bit vectors with 16 coordinates. So what should the shape of the matrix be? (16 by 11), exactly. So it needs to have 16 rows because each row is going to produce, it's going to write a bit in my output stream, and 11 columns because every time I write a bit, it's acting on these 11 coordinates, right? So 11, so when a matrix acts in a vector with 11 coordinates, it must have 11 columns, just for that action to be like well-defined for things to match. Okay, so we sorted on the dimensions of the matrix, 16 rows and 11 columns. And what I want is for this matrix to write out what we just said, the process that we just described for the parity bits. So in particular for the for the first, like I said, let's just ignore what's going to happen on the X bit, which is the top left corner. I've written 16 rows just to match with the 16 boxes in my grid. But since I haven't sort of specified what happens to the top left box, we can basically just ignore that row for now. But for the very first bit, remember, is the value of the blue parity check matrix. So what that's going to do is it's going to go to the message and it's going to pull out the relevant locations that play into the action of the blue parity check matrix, the blue parity check bit. And it's just going to add them up mod 2, because remember that the parity check bit, all it's doing is it's saying that I will sum up the number of ones in these locations and I'll sum them mod 2. What does that mean? Well, if you have an odd number of bits in these blue locations, except for 1, because 1 is the location of that parity check bit. So 5, 9, 13, 3, 7, 11, 15. If these 7 locations together have an odd number of ones, then what should the value of the blue parity check bit be? 1, because I want the total number of bits in these 2 columns to be 0. That's, well, at least that was my mechanism. On the other hand, if the total number of ones across the locations 5, 9, 13, 3, 7, 11, 15 was even, then what should my blue parity check bit be? 0. Perfect. But that's exactly the mod 2 sum of these 7 entries, right? If you take the mod 2 sum of the bits in the locations 5, 7, 13, 3, 7, 11, 15, that's going to be a 1 if the number of ones here is odd and 0 otherwise. So just taking that mod 2 sum gives us the correct value for the blue parity check bit. Does that make sense? Great. So in this row of the matrix, all that we need to do is just set ones corresponding to those locations in the message. If you can just filter out those locations, the matrix action will just snap it to the mod 2 sum and give you the value of the blue parity check bit. And exactly. And now for the second row, that's going to be the orange parity check bit. And that's just, I mean, you can validate these numbers offline. It's not terribly important. I mean, it's possible that I've made some typos, so you can go back and check. But the locations of these ones are really designed to pull out the relevant bits from the input stream. Okay, so in this case, it's pulling out all the bits at the locations that we said the orange parity bit will act on. The third bit is, okay, this is the 4th row of the matrix, which is the top right corner of our grid. What was sitting in the top right corner of our grid? Do you remember? Let me go back. So what was sitting in the top right corner? Is it a redundant bit or is it a bit from the message? Okay, it's a bit from the message. And which bit from the message is it? It's the first bit from the message. So in my matrix, all I need to do for the 4th row is pull out the first bit of the message and just write that to my output. So how do I do that? What should the 4th row look like? One followed by all zeros. Exactly. It's 1 followed by all zeros because you just want to pull out the first bit of the message. That's it. Yeah, perfect. And then you come to the first bit of the second row, and that's the green parity check matrix. So that again pulls up the relevant, it pulls up everything in the 3rd row and the last row. Sorry, everything in the 2nd row and the last row. So visually, hopefully you can see that that's, with the columns, the locations were a bit confusing, but everything from the message in the 2nd row and the last row is what is highlighted on top. And it's those locations that are ones in the in the fifth row. The sixth, seventh, and eighth rows will have to pull out the second, third, and fourth bits from the original message. So that's just continuing to be this identity kind of structure. Next, we have the red parity bit, which just pulls up the entries from the last two rows, the 7 entries of the message from the last two rows. So it has all ones towards the end, and that gives you the value of the red parity bit. And then we have, basically, we just spew out the rest of the message because now we are done with all the parity bits. So when you take this matrix and you apply it to a 11-bit vector, you get the 16-bit vector that you were looking for, except the first bit is unspecified. You can make that all ones if you want, if you're convinced with the exercise that, if you add the parity check for the entire message, then you can catch the situation that you can detect that there is more than one error. So if you want to do that, you can. The other thing is to just chop it off. So if you look at the presentation in the miniature, they actually do it for not the 11-16 combination, but they do it, I think, for the 4-7 combination. So a message of length 4 blows up to a message of length 7, and they don't make it a message of length 8. So they will not have this top row in what's called the generating matrix. So this is called the generating matrix for the code, for reasonably obvious reasons, because if you take the generating matrix and you apply it to your message, you get the coded message. So it generates the code for you. So the generating message is very useful for the sender who is trying to encode the message so that it can be sent across the stream. And this is just a color coding to remind ourselves about what this matrix is actually doing. I leave it as an exercise for you to think about whether, it would be fine to just rearrange these rows to make them look nicer so that you have the identity matrix at the bottom and all the parity check stuff pulled up on top. The only reason I wrote it this way is so that we could relate it to the structure that we had before. But I'll leave it to you to think about what happens if you just swap out some of the rows. Will everything still work as it is? Okay, so this is the generator matrix. Let's just look quickly at another matrix, which is useful at the receiver's end, because they have a message and they now want to decode it. Okay, and they want to figure out where the error is, if there is an error, and so on. Okay, so I know that we've just about hit the half-hour mark, but this should not take us too much longer. So what do I have on the screen right now? Well, I have all my parity check constraints. So the first row is the blue bit talking about, I've implicitly used X to denote my message. So X1 is the first bit from the message, X3 is the third bit, X5 is the fifth bit, and so on. And so basically I've taken all the odd numbered bits. And okay, so you can basically imagine that these Xi's simply denote the locations that the 4 parity bits were acting on. So the first one corresponds to the blue bit, which was just picking up alternate locations and was looking at the odd numbered positions. The second row corresponds to I think it was the orange bit that picks up everything, all the locations which in binary had the second last bit as 1, essentially the last 2 columns of our grid. The third one is it's the green parity bit, which picks up the second row and the last row, and it's basically those locations. And the last row corresponds to the red parity bit. I have no idea why I didn't color code these equations. I should have done that. But anyway, the last row corresponds to, all of the last 8 positions adding up to 0. So these are basically constraints, and this notation here, the O plus, is basically the XOR notation to remind ourselves that we're doing addition mod 2. Do these parity check constraints make sense? Do they at least look familiar and look reasonably okay? This is just an expression of what our 4 redundant bits were doing. Okay, perfect. Now, the point is when we have such constraints, we can actually write them as a matrix. You might, in fact, your first encounter with matrices may have been in the context of modeling linear equations. Like you write down your linear equations, which have which describe a set of constraints over a set of variables. And it's just convenient to express them as AX plus B, A times X goes to B or something like that in matrix form. So we're going to do just that here. We're going to write out these constraints as in matrix form. So this is called the parity check matrix. And this is basically a number of checks over 16 variables. Again, I have that implicit 0th location, which you don't really have to care about. So again, in the standard representation of the Hamming code, that first column would not be there. I'm just being OCD about being consistent with the grid earlier. So I have an extra column there. But anyway, the parity check matrix basically describes the parity constraints that we just put in. And what does this act on? What sort of a vector does it act on? It acts on messages received by the receiver. So messages that were transmitted over the channel. So you can think of those as, I think I conflate the use of the word message for both the thing that we want to send and also the thing that we actually send, which is the padded message. So I think the padded message is what I should be calling the coded message, because it's the message plus all the extra parity bits that have been added. But regardless, you can see that the parity check matrix has 16 columns. So you can imagine that it acts on a 16-bit vector. And let's ask ourselves, what are all the vectors that the parity check matrix sends to the 0 vector? In other words, what is the null space of this parity check matrix? I think if we get this, I'll kind of be reassured that we have sort of made sense so far. So imagine the parity check vector acting on x1 through whatever, x0 through x16, and everything goes to 0. That means that all of these constraints are actually satisfied, right? So the blue bit is happy, the orange bit is happy, the green bit is happy, and the red bit is happy. That's what happens. That's what it means for the parity check matrix acting on a 16-length vector to be sent to an all zeros vector. So we do have a comment in the chat saying that there were no errors. So is everybody in agreement with that? Okay, technically an even number of errors, but let's assume that we're still in the regime of at most one bit got flipped. So in that case, this would definitely correspond to no errors, because the only way you can have an even number of errors and at most one error is if you have 0 errors. Is everybody okay with that? Okay, awesome. So the set of all valid words, that is words where the channel did not mess around, the message is intact, the redundant bits are intact. Those are all the vectors that sit in the null space of the parity check matrix. So these are the vectors we are happy about. And so as far as the decoder is concerned, the receiver is concerned, they're going to get some string of length with 16 coordinates, or 15 as you please. So that's W. And well, of course, as a receiver, I have no way of knowing if W is corrupted or not. I know because of the assumptions we have made that at most one bit is corrupted, okay? But I don't know if one bit is corrupted. And I also don't know if one bit is corrupted, where is the corrupted bit, okay? These are things that I don't know just by looking at the message that I got. So what I'm going to do is I'm going to apply the parity matrix on W. And if there was an error, we can separate out W as V plus E, where V is the valid message and E is an error vector, which just has 1, 1 in the location of the bit flip. Okay, so I think I probably have a slide which is more pictorial coming up, but let me just break this up a little bit. Or maybe let me just skip ahead to see if this makes sense. Okay, no. So, okay, maybe this tall vector that you see here is typically what an error vector looks like. Okay, so you have some genuine message and the channel decided to flip a bit. So you can write down your genuine message as this one vector, and you can add to it an error vector, which has exactly 1, 1 at the location that the bit was flipped. Okay, So is it clear that that's what W looks like if the channel has messed around with it? W equals V plus E. Is this part fine? Okay, great. So now if we look at the action of P, so let's just expand this out. So what do we know about PV? V is a genuine message. So we already know that P maps all genuine messages, where nothing has flipped. We already know that all of those are sitting in the null space of P. So what is PV? Yeah, PV is the all zeros vector. Absolutely. And then we have PE. That's all that's going to be left. But what is the action of P on an error vector? What is the output here? You can just imagine sort of rotating this vector and running it through running it through the whole matrix. Do you see that what it pulls out is what? Well, in this case, it pulls out 0, 1, 0, 0. You're absolutely right. In general, an error vector will simply pull out a column of the parity check matrix. But whatever column it pulls out, notice that all the columns of the parity check matrix are not only distinct, but they actually read off the locations in binary, which is not surprising because that's how we set our parity bits to begin with, right? So we go 0, 1, 0, 1, 0, 1 on the first row, 0, 0, 1, 1, 0, 0, 1, 1 on the second row. Now blocks of 4 zeros and 4 ones on the third row, and half zeros and half ones in the last row. So if you just, I don't know, rotate your head or your screen 90 degrees, you're going to be able to see that the columns of the parity check matrix are just like basically 0, 1, 2, 3, 4 up to 15. And what gets pulled out when you apply the parity check matrix on the error matrix is precisely the location of the error. Okay, so that's something that, yeah, that's pretty cool, isn't it? So and basically essentially the action of the parity matrix on the error matrix is a reflection of basically which bit combinations are unhappy. So it basically precisely points to the location of the error. So you can look at the output of the parity check matrix, read it off basically in decimal to identify the coordinate where the flip happened. That actually maybe, I mean, if you want to be really sure that that's the mechanics, that's what is actually happening, like that's where the flip happened. I think that might require like a couple of additional lines on pen and paper, but at least at the level of being intuitively convinced that this is what's happening. Maybe I'll request for a +1 in the chat if this picture makes sense overall. Okay, great, thanks. I think the way it's explained in the book is to say that when you're mapping, so if we go way back in our slides, okay, maybe I'll just, before I do that, I'll just show you quickly, just to be at parity with what is there in the book. So if you look at miniature number 5, what they actually describe is the 4-7 Hamming code. And let me just quickly walk you through this. So in the 4-7 Hamming code, we are sending code words of length 7. That is, this is the word that has the message and the redundant bits all packaged in together. So you have 7 locations to do your thing, of which 4 are going to be true message bits and 3 are going to be error bits. Okay. Now, what I've written out here is the 7 locations of your message, the 7 indices of your message in binary. And if we just follow the recipe that we followed earlier, well, what we are going to do is, well, look at all the bits, look at all the locations whose last bit is 1. These are all the alternating odd numbered locations. So and then look at all the bits whose middle bit is 1. So these are the, I don't know, these are some interleaved locations. And then look at all the bits whose leading bit, the most significant bit, is 1. This is the bottom half of the pile. So we are going to set our parity bits to be the first red bit, the first blue bit, and the first green bit. Okay, so in our string, I'm going to call these bits X, Y, and Z. And the remaining 4 bits, that's where we're going to squeeze in our message, A, B, C, D, right? So now our parity checks are basically going to be X equals A plus B plus D. Why is that? Because X is trying to pull out the locations of those red numbers, 0, 1, 1, which is A, 1, 0, 1, which is B, and 1, 1, 1, which is D. Similarly, the blue bit is going to be reflecting the parity of what's at the 0, 1, 1, 1, 1, 0, and 1, 1, 1 locations. That's going to be, well, let's see, that's going to be A, C, and D. So that's the bit Y, and Z is going to pull out the parity of the last 3 locations. So that's B plus C plus D. So the way this is described in the miniature, I think they start off by saying, well, let's take A, B, C, D, and let's tack on X, Y, Z defined as follows. And then they say, well, everything else works out. And sure enough, it does. All the calculations go through. But it does leave you wondering, A, why do the calculations go through? And B, how does this generalize further? And technically, the book does have a comment about how it generalizes, but it's not really obvious because here, for example, it might look like what's happening is that you're dropping one of A, B, C, D. So there are 4 bits and you drop one of them at a time to get 3 parity checks. It's really not obvious what's the pattern here that generalizes to a longer message, which is why we went through this slightly longer detour of trying to view it in terms of, well, the semantics of what these locations really mean and thinking of it in terms of binary search, which I think is a really cool angle to put on this. And okay, I think what I said, I will just go back to, and this is the last thing I will say with apologies for going over time. But if you remember, we said that the encoding process can be thought of as a map from F2K to F2N that basically maps things in a manner that's far apart. So in particular, if you do have a code that corrects for 1 bit, if you look at the space around the 0 in the target space, any other vector should be at a distance of at least 3 from the 0. So in general, basically you want to in general keep a t-ball around your things that have pre-images. You want to keep a t-ball around it clean. And that would mean that the distance between any pair of code words should be at least 2t plus 1, right? Because otherwise you sort of have your balls colliding, which is not nice. So the terminology in the book to say that the parity check matrix that you get for the 237 Hamming code or the generating matrix that you get, they write out both of those. The fact that forms a valid code, I think the way they say it is by just arguing that this distance property in the code space is satisfied. And they do that by basically showing that any vector which has 1 or 2 bits will not get mapped to 0. And that's easy to see from the parity check matrix because, there are basically all the columns are distinct and you chop off the leftmost column because we don't really need it. And you'll see that there are no 0 columns and there are no 2 columns that are the same. So if an input vector has, just 1 or 2 ones, then they're not going to get mapped to the 0 vector. So the 2 radius around the 0 vector is kind of clean. That's the language that's used in the book. I think I did rush through everything that I said in the last couple of minutes. So I totally understand if it didn't make sense, but I only said it so that if you're going back to the miniature and reading it, or if you've already read it coming in, then this is just to quickly justify that we're really doing the same thing. I just used slightly different language and visuals, but I didn't cheat too much. It's really the same thing that's there in the book. So Okay, in the forums, I think I have posted a link to a chessboard puzzle, which seems awkwardly related to what we have done here. And there's a fun video of Grant Sanderson, and who is behind 3 Blue 1 Brown, and Matt Parker, who is behind Stand Up Math, two very popular YouTube channels, collaborating on what's called the Almost Impossible Chessboard Puzzle. And at some point, Grant jokes that this puzzle is like the opposite of error correction. It's anti-error correction. And it leads you to thinking about why. And in fact, solving the puzzle motivated Grant to also make some videos about the Hamming code. And that's linked to in the discussions as well. I think that's a really great combination of videos to watch if you found any of this intriguing or pretty or both. And the chessboard puzzle, with everything we've discussed so far, and if you haven't seen it before, is a great puzzle to geek out on without spoiling for some time. So highly recommended as a sort of next thing to look at from here. And tomorrow we will be back with miniature number 6. This is all that I will have to say about miniature number 5. And we are well over time. So for everybody who's stuck around till the very end, thank you very much. We will... well, at least I will stop here, but if there are any questions or comments, I would be very welcome. All right, so I think given the official timing and given that we had a nice discussion in the chat right through, maybe this is a good time for me to stop the official stream with a thanks to everyone who joined or is watching later. So we will continue tomorrow.